Okay, welcome. Thanks to everybody for showing up this evening. As you saw there, I think we've solved the riddle of how many professors does it take to operate the AV equipment. So I think we were at 3. So there's no quiz on that later, though. All right, my name is John Culton. I'm the director of the Andy Thomas Center for Space Resources, and it gives me fantastic pleasure, in conjunction with Nelson Tansu, the head of school for the Triple E school here, to welcome again a couple of our friends from the Jet Propulsion Laboratory in California to our campus. I'm going to read the introductions for both of our amazing speakers tonight, and then hand the mic over to the interim JPL director. And they'll hand off between their two presentations for us. You will fortunately be able to see a University of Adelaide person in the front the entire time, as I will be here to flip slides. One thing to note, we will take questions at the end of the presentations, so we will have an opportunity for Q&A once the speakers are complete. So again, it's my pleasure to introduce Interim JPL Director Larry James. He was appointed Interim Director of the Jet Propulsion Laboratory in August of 2021 after serving as Deputy Director and Chief Operating Officer since 2013. As the laboratory's Chief Executive Officer, he is responsible for the day-to-day management of JPL's resources and activities. This includes managing the laboratory's solar system exploration, all business operations, and 6,000 scientists, engineers, technicians, and business support personnel, generating $2.6 billion in annual revenues. Prior to his retirement from active duty in 2013, then Lieutenant General James was the U.S. Air Force Deputy Chief of Staff for Intelligence, Surveillance, and Reconnaissance at the Pentagon, where he led more than 20,000 ISR officers, enlisted and civilians across the Air Force enterprise. Lieutenant General James received his Bachelor of Science in Astronautical Engineering from my alma mater, the U.S. Air Force Academy, where he was a distinguished graduate, and his Master of Science in Aeronautics and Astronautics from the Massachusetts Institute of Technology in Cambridge, Massachusetts. Following Larry will be Suzanne Dodd. Susan Dodd is JPL's Director of the Interplanetary Network Directorate. She has over 30 years of experience in spacecraft operations, serving as project manager roles on the Voyager interstellar mission, the Spitzer Space Telescope, and the Nuclear Spectroscopic Telescope Array. Most recently, she led the Operational Missions Office within JPL's Astronomy, Physics, and Space Technology Directorate. Suzanne worked at Caltech for 11 years as manager of the Spitzer Space Telescope Science Center and as manager of the Infrared Processing and Analysis Center, NASA's Multi-Mission Center of Expertise for Long Wavelength Astrophysics. She has also worked in the area of mission planning and uplink on the Cassini mission to Saturn, the Mars Observer Project, and Voyager 2's flybys of Uranus and Neptune. Susan has a bachelor's degree in engineering and applied science from Caltech, a bachelor's in math and physics from Whitman College, and a master's degree in aerospace engineering from the University of Southern California. She is the recipient of multiple NASA awards, my favorite being the Outstanding Leadership Medal. So with that, I'll turn the floor over to our more interesting speakers. Sir, the floor is yours.
All right, well, good afternoon, and thank you for joining us here today. It's always a pleasure for me to come to Australia and just really share some of the great work that we're doing at JPL and at NASA, but also the work that we partner with here in Australia. So appreciate you all coming out here today. And what I like to do when I first start off is just show you a video about JPL. And I'll be honest up front, it's very self-serving in terms of talking about JPL. But I think it gives you a sense of what JPL is all about in terms of our focus on science, in terms of our focus on answering those hard science questions that no one else has answered and doing things that no one else has done. But it gives you that perspective from each of the people who really make that happen. So you'll just see about a 3-minute video that kind of kicks us off, and then we'll dive in more deeply from there.
What does JPL do?
It's the most unique place to work on Earth.
Our charter is to do things no one has done before.
We do what no one else even dares to dream about.
Imagination and innovation are crucial in being able to do the kind of work that we do.
Innovation comes from people, but it also, I think, comes from structure and from the environment. If you can provide people with the appropriate tools, the appropriate workspace, the appropriate environments, you're also going to get a higher innovation output.
One of the things that makes the JPL environment so special to work in is that even when you first walk on lab, it feels like a campus.
And you walk around, you hear people talking about their work.
What would be the best way to get a subsurface vehicle beneath the ice of Europa? And you're thinking, those people aren't just talking about it because they saw it on a movie somewhere. It's because they're really trying to figure out how to do it.
JPL is an incredibly diverse place.
There's thousands of people here with big brains.
Planetary science, answering these big questions, you need chemists, physicists, astrophysicists, biologists, and then you need everyone on the engineering side to actually build the things that you need to answer the questions.
People know so much about so many different things that if I'm looking for an expert in a particular field, engineering or science related, I can probably find them at JPL. I don't have to pick up the phone, I just have to walk down the hallway.
Science is all about asking questions, and engineering is all about finding solutions. And so it makes sense to marry these two things together and try and answer the biggest, toughest, most difficult questions we can come up with.
What does JPL do? JPL builds the tools for exploring space.
The boldness of my colleagues is inspirational. The scope of the questions that they want to answer and the courage with which they go about tackling these big questions.
The passion of the people, the drive, the enthusiasm, and just the intelligence, the intellect that people throw every day at every problem that comes across.
Given a very challenging problem, please do this thing that's never been done before, that we don't know what to expect, that there's a huge uncertainty involved with. Most people would be terrified by that problem. I think those are the problems that we salivate over.
We shouldn't do something because it's safe and easy. We shouldn't do the thing that everybody knows how to do. We should push the boundary, and even if that means we might fail, we might succeed too.
I've never met anybody here that says, well, it's too hard. We all sit down and we just start crunching the numbers and figuring out how to get it done.
It's a journey. It's not necessarily an end destination. It's the whole way in which you're getting there.
It's a very liberating kind of environment to be in because you don't have to be so afraid of mistakes.
To recognize that we're doing science inside the solar system, outside the solar system, science focused back on Earth.
Our missions have a goal of helping humans understand more about the universe, and I think that's pretty amazing.
JPL has enormous respect for a good idea, and if you have a good idea, this is the place to bring it to fruition.
JPL is a special place because it allows people to have careers that are only limited by their imagination.
Well, there certainly is this drive, I think, from the human race to go explore, and not everybody's involved directly with that effort. As the years go by when you're at JPL, it becomes very clear that it truly is a privilege to be here.
This lab is leaving a legacy for not just the country, but for the world. And someday, if we ever do find that exoplanet that has life on it, or encounter some other solar system outside of ours, this is a place that's going to do that.
After that, I usually don't have to say anything, but you'll get a few PowerPoint slides that tell you a little bit more in depth about what's going on today with JPL. So just a little bit of history. We trace our roots back to 1936 when a bunch of Caltech students and professors tried to figure out how to build rockets. And they were doing that on the Caltech campus at Pasadena, and they kept having explosions in the lab. And so they said, please move. So they literally moved up into the arroyo above Pasadena, which is where you see the little, what we call the suicide squad there on the top left, trying to build rockets. So we trace our history to Halloween Day, October 31st, 1936. And then in the second slide there, you see that during the war years, World War II, because we were one of the nation's experts in building rockets, we were taken over by the Army. So we were operated by the Army. They built a bunch of facilities for us to build rockets and test rockets and aero chambers and those sorts of things. And we supported the war effort. After the war stopped, we were reverted back to Caltech. And then Sputnik was launched. And so Caltech said, well, we know how to build rockets. Let's see if we can put something on the top of those rockets. And so Caltech built America's first satellite, Explorer 1, which was launched in January of 1958. And you can see that iconic picture there in the middle. Holding up a model of Explorer 1 on the left is Dr. William Pickering, who was the director of the lab at the time. In the middle is Dr. James Van Allen. Anybody know what was named after him? Yeah, the Van Allen belts, which were discovered by Explorer 1, an experiment he had on Explorer 1. And then on the right there is Dr. Wernher von Braun, who helped build the rocket that got us into orbit. So it was a great day for the nation and for America and certainly for the world as we launched Explorer 1. And after Explorer 1 was launched, NASA was created, and they asked Caltech if JPL would be their research lab. So that's who we are today. We're NASA's research lab, but we're a part of Caltech, and I'm a Caltech employee. Susie's a Caltech employee supporting NASA work. And of course, Susie's going to tell you all about Voyager, so I won't belabor that, but humanity's first interstellar spacecraft outside the solar system. And then we really focus, and you saw in the video there, we look a lot back at the Earth. We have a lot of missions that are exploring our planet. Mars is certainly an important component of what we do because of its nearness to the Earth as well as its potential habitability in the past. And then we look out beyond the solar system. You heard mentioned the telescopes that look out beyond the solar system. And certainly exoplanets is really a new area of exploration and excitement in astrophysics. So those are the areas that we do science in. We answer those hard science questions. I'm not going to walk through all of these, but it just gives you a sense of the current missions that we have operational right now. Multiple missions around the Earth, multiple missions at Mars, multiple missions looking out beyond the solar system. And just highlight a couple maybe. Again, you hear about Voyager. We've been around Mars for decades. You've got the Mars Odyssey mission there that went into orbit around Mars in 2001, still operating, still providing data for us as we operate around Mars. You saw maybe one of the telescopes there in the video, New Stars and X-ray telescope that's peering into black holes, using X-rays that are coming out of black holes to help us understand that. But again, I'll touch on some of these, but you can see that there's a host of things that are currently operational. And we also have major payloads down here on the bottom. One that I like to talk about is CAL, which is the Cold Atom Lab. That is a laboratory we currently have up on the space station that is producing Bose-Einstein condensates that last for significant periods of time. In the Earth's gravity, we can only create Bose-Einstein condensates for microseconds or just a fraction of a second, whereas in 0G, we can keep them together for much longer. And that allows us to really study this other fundamental piece of matter, Bose-Einstein condensates, that we really don't know a lot about, but they can be used for a lot of quantum instrumentation and those sorts of things. So again, we also have 3 Nobel Prize-winning principal investigators on that experiment. So they're getting a lot of great data, and you'll see a lot of good papers coming out of that. So let's talk about the Earth. When you think about JPL, a lot of people think about Mars, or they think about going to Saturn or Jupiter, but the reality is we have a significant set of spacecraft that are orbiting our Earth and really trying to help us understand what's happening to our planet. So I'm just going to highlight some of those. This is a mission called GRACE. GRACE is a gravity measuring mission that literally will measure the changes in gravity as it flies over the Earth. And so how does it do that? It does that by having 2 satellites fly in formation. If you saw that in the video, the oceanographer said JPL has enormous respect for a good idea, and you see 2 satellites flying over the Earth in formation. Those were the 2 GRACE satellites. And they literally determine change in mass. They literally measure gravity by measuring the change in distance between the 2 spacecraft. So you have a lead spacecraft that would fly over a mass, and if that mass is large, let's say like the Himalayas, it literally pulls on the spacecraft and speeds it up. But the trailing spacecraft hasn't reached that point yet. It's hundreds of kilometers away, and so it doesn't speed up yet, so the distance changes. So over time, the distance literally changes as we fly over different masses of the Earth, and as those masses change, we can detect that difference based on what we had measured in the past. So now, class, you're going to get a little video that will show you how this happens. So there's no audio to this other than the funky sound that doesn't happen in space. But so we have a microwave system, a microwave signal that's going between the two spacecraft, as well as a laser system that's measuring the distance down to nanometers between the two spacecraft. And so as the front spacecraft comes over a mass, and you'll see this indicated here shortly, you'll see kind of the frequency shift, and that's indicating that the distance is changing between the two. And then the trail spacecraft will speed up and it'll catch up to it. So over time, the scientists take all those measurements and determine where the mass is on the Earth. And so there you can see that the lead spacecraft is approaching a mass, a hill, and now it pulls out ahead, and the trailing spacecraft catches up. So we're constantly measuring the distance between those two spacecraft in order to get a map of the mass or the gravity of the Earth. And what does that tell us? Well, it tells us what's happening to our Earth in terms of, for example, loss of the ice sheet in Greenland. So as you get less and less ice in Greenland, you have less and less mass, and therefore we can measure that change in mass over time with the spacecraft. Same thing with the Antarctic. So here you can see the diagrams, the slides. So since roughly 2007, where we started here with ice mass, you can see pretty significant change in terms of ice mass loss in both of these areas. And so this really helps our scientists have this long-term understanding and long-term map of what's going on with our planet. They feed that into their models and helps us to be able to better predict what the future will be like. This is the mission you saw at the very end of the video, which is called SWOT, Surface, Water, and Ocean Topography. And so the whole water topography of the Earth is very important, and understanding the water cycle is very important. I come from California. We're in the middle of a multiple-year drought. I know in Australia you have significant periods of drought. And so really trying to understand the water cycle and what's happening is very important. And so what this mission is going to do is going to measure the height of the oceans, which is very important in understanding, again, what is happening with ice sheet melting and those sorts of things. But it also is going to measure ocean currents as well as freshwater body heights and currents. We've been measuring heights of oceans for decades, primarily with microwave radar satellites. Those work very well for the ocean, a very salty environment, but microwave doesn't reflect well off of fresh water. And so this is a whole new generation of spacecraft which will use two radar beams which create radar interferometry on the surface of the water, and that allows us to measure freshwater body height as well as the currents in the freshwater bodies and the ocean. So we'll be able to gather a lot more data from this spacecraft than we've ever done in the past with respect to those components of the water cycle. This is also a partnership with France, the French Space Agency. JPL built the payload. France is providing the payload bus. In fact, the spacecraft is in France right now. It's been integrated with the satellite bus. It's going through environmental testing. It will be shipped back to the United States in September, and then we'll launch it from Vandenberg Air Force Base in November. So if anyone wants to come to California and see a launch, this will be up. Another couple of missions that are up on the space station, I talked about the Cold Atom Lab, but these two missions are focused really on Earth science. One is called EcoStress, and that is a mission that essentially it's a very sensitive infrared sensor, and what it's actually doing is measuring plant health. And you ask, well, how does an infrared sensor measure plant health? And what it does is when plants are healthy, they are absorbing water. That water is transpiring out through the leaves, and that cools the plant off. If they're not healthy, they're not absorbing the water, or if they're in a drought condition, they're not absorbing the water, so there's no water to transpire out of the leaves and they're hotter. So by literally measuring the temperature of a plant, you can kind of get a good sense of the health of the plant. And because it's a very sensitive IR sensor, we've also been using it to map wildfires. I know that's one of the areas of focus here in Australia is understanding wildfires, mapping them, doing that from space. And so this sensor has been very helpful in California for giving California firefighters a sense of what's going on with wildfires based on this IR sensor. Also, another system looking at the Earth is our Orbiting Carbon Observatory 3. This is on the space station, obviously, on the Japanese experiment module. And what it's doing, it's measuring carbon dioxide creation as well as absorption. So where is carbon dioxide being created? What are the big creators like when they do the crop burning in Australia, or not Australia, sorry, in Africa, or the ground clearing, you'll see a lot of carbon dioxide produced. But we also see where it's absorbed, like in the rainforest and those sorts of things. So again, that entire carbon dioxide cycle is extremely important for understanding our planet. And scientists take that data, they feed it into their models and help them understand better what's going on with the carbon dioxide content of the Earth's atmosphere. So a couple of missions that are doing a lot of great work for understanding our planet. And then this is another spacecraft that's currently being built at JPL, NISAR, which is the NASA, I stands for Indian Space Research Organization, Synthetic Aperture Radar. So this is a partnership we have with India, again, to build a dual band, S-band, L-band synthetic aperture radar satellite. And what that will really do is kind of map what's going on with the surface of the Earth. So with these two radars, we can map things like what's happening with our coastlines. We can map biomass, so what's going on with biomass changes in the rainforest or other areas like that. We can map changes in Antarctica and Arctic and Greenland and those sorts of things. So again, very important data for our Earth scientists to plug into their models and again understand better what's happening to our planet. This mission, this is the payload end, this is the radar end right here with the receiver reflector up here. So this payload is actually in the clean room at JPL right now. We will ship that over to India early next year, and they will integrate it to the payload bus, which they are building, and then we will integrate it on top of an Indian GSLV launch vehicle and launch it out of India in January of 2024. So a great international partnership with India that will provide some great new capability from a synthetic aperture radar perspective. So we've started with Earth. Now let's move on to Mars. Why is Mars important? I think we all kind of understand that. Very much like Earth. We know it had water in significant quantities in the past. Elon Musk wants to go live there, etc. So our first major rover was Opportunity, launched in the early 2000s, and primary mission completed in 2004. But this really kind of showed us that we could indeed operate rovers on Mars and we could gather good science from Mars. And then, unfortunately, our rover died in a major dust storm because it couldn't get enough sunlight to power the solar panels and keep it operating and keep it warm. But it operated for, I think, 15 years, Spirit did. So just an incredible mission in terms of those first rovers doing science on Mars. Curiosity has been our workhorse on Mars since 2012. A lot of incredible discoveries. You can kind of see where it's driven all over the place there. It landed in Gale Crater, which is nice and flat. It's gradually been working its way up kind of the hill there from the bottom of Gale Crater. It's traveled over 17 miles on the surface of Mars, and roughly it'll be a 10-year anniversary this August that it's been operating. As I said, it's shown that there was a lot of water on Mars at one time that lasted for millions of years. It's found organics. So really rewrote the science books on Mars with respect to what we knew about Mars in its past. So just an incredible mission, an incredible topography there. So we can actually take selfies with our camera on the end of our robotic arm. And so that's one of the sand dunes that we had to navigate around. Our next mission to Mars after Curiosity was called InSight. InSight was not a rover, but it was just a lander, and its whole purpose was to measure seismic activity on Mars. And why do we do that? Because scientists really didn't know anything about the core of Mars. We know a lot about the core of the Earth, but we didn't really know a lot about the core of Mars. And you can literally map the core of a planet by measuring the seismic activity as it kind of goes through the planet. And over time, you can start to build a picture of how those seismic waves are modified through the core. And you take enough measurements, you can actually build a picture of Mars' interior. So that was the entire purpose of the mission. Again, a partnership with France. France actually provided the seismometers that went on this mission. Really, they were the key instrument. And the seismometers they provided could measure movement to the half of a width of a hydrogen atom. I don't even know how they can do that, but that's how sensitive those seismometers were. This mission has continued to operate since 2018, and there's already been multiple papers published that talk about what the core of Mars is like. So it's been very successful in helping us understand the red planet. Interestingly, I know there's a lot of interest in CubeSats and small sats, and a lot of folks are building those today, and they're doing incredible missions in science. These were the first interplanetary CubeSats called MARCO, and what they were they were really just radio relay CubeSats, because when InSight was landing on the surface of Mars, our orbiting spacecraft that normally provide radio relay were not in the right position to give us information in real time as we were landing the spacecraft. So the crazy people, the crazy engineers at JPL said, well, can I build a CubeSat that could act as a radio relay at Mars? And we said, go for it. And so they built two of them. One is just a backup for the other. So I'll show you a little picture here, but that's our technicians building the MARCO CubeSats, and really all it is a receiving antenna on the bottom and a transmitting antenna on the top that took the data from the InSight spacecraft as it was landing and translated it back to the Earth. And so they worked perfectly. Both of them worked. We got the data in real time. We were able to watch the mission land on Mars, and amazing success for a CubeSat out at Mars. So we also put just basically a GoPro camera on the thing. These were kind of cheap. And we got some really cool pictures as we approached Mars. You can see Mars right there, and you can see the solar, or it's the combined solar panel and radio antenna. But this is MARCO headed to Mars and flying by it. So worked perfectly. So you can do a lot with CubeSats these days.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
This is our mission last February.
Indicate chute deployed. The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converged. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars. ready to begin seeking the sands of past life.
Okay, well, that never gets old for me. So that was our landing of our Perseverance rover. And what is its mission? Well, its primary mission is to actually cache samples in titanium tubes about this big for storage on the surface of the planet, which we will ultimately bring back to Earth. It also has some very good instruments on board at the end of the robotic arm, which will allow us to do X-ray spectrometry and those sorts of things. But primarily what it's doing is collecting samples. This is a picture from our helicopter. You may have heard about our Mars helicopter. We just took this on April 19th. You heard the back shell separation in the video. Well, this was the back shell that encompassed the rover as it came into the atmosphere. And we got a picture. We flew the helicopter over the back shell as well as the parachute. So that's what it looks like after it crashes on the surface of Mars. So that was a pretty, we'd seen it from orbit, but we'd never had an up-close picture of the back shell as it crashed. So nice picture from Ingenuity. So Perseverance is well over 400 days. Again, we landed on February 18th last year. We've driven over a kilometer, over 10 kilometers, and we've taken now 8 samples in our tubes. We've got 8 rock cores, 1 atmospheric sample, and then we have just kind of a witness sample. One of the great things about Perseverance is we've added a lot of artificial intelligence, which allows it to drive autonomously, because we want to cover a lot of ground as we look for good places to collect these samples. So that's just kind of a nice composite of all the driving we did on one of our drives the week of late April, driving around the surface. And so it's got the intelligence on board to really steer clear of obstacles, as well as if it gets into something that's trouble, it'll just stop and wait for us to give it the right commands. So again, very complex system. You heard on the video something called terrain relative navigation. When we landed Curiosity, we went into Gale Crater. Gale Crater is nice and flat. We really just came in ballistically. We released it in the upper atmosphere, and we calculated exactly the time and place to release it, so we would come into the Gale Crater where we felt we could land safely. But for Perseverance, because it was collecting samples that the scientists wanted to be brought back to Earth, they wanted to go to a much more complex environment, which is also a much less safe environment to land, i.e. not very flat. So that's when we went to Jezero Crater, and the reason we go there is because it's literally a river area that flowed into a large sea or lake. But as you can imagine, with rivers flowing and those sorts of things, you got cliffs and rocks and boulders and those sorts of things. So we had to be able to look down at the surface of Mars and navigate as we came in on the rockets, on the landing system, and avoid any hazards. And that's when you heard the landing vision system has converged, and we're executing terrain relative navigation. That's what all that was for, to ensure we could find a safe place to land. We wouldn't land on a boulder and crash or whatever and end the mission right up front. So again, scientists are very happy. We kind of went over into one area because it looked very interesting to the scientists, and we drove around there and took a bunch of samples. And now we're headed up into this area, which is more toward the river delta. So this is what we call Hawksbill Gap up here, and the rover's slowly making its way up into that area, which is more of the river delta area, and that's where we'll be taking some additional samples here probably in the next month to 6 weeks and continue that campaign. What we're also doing right now is those 8 samples that we have taken, one of the things we want to avoid is that if something should break on the rover and it suddenly dies and the samples are still inside the rover, we've lost the mission. So they're going to take probably those 8 samples here in the near future and place them just on the surface of Mars in a known location and just leave them there, so that when we go back to pick those samples up, we'll have something to pick up if something bad should happen to Curiosity in the near term. So you'll probably see us dropping those samples off here in the next month or 2 in a nice flat location where the return lander can pick them up. This is our helicopter. This is Ingenuity, its 3rd flight. The first 2 flights were just straight up, straight down. This was a little more interesting in that we went up and then we translated. So this was just really a technology demonstration. Can you build something that can fly on Mars? You know, Mars' atmosphere is 1% of the Earth, so it's like trying to fly at 100,000 feet. And it's, you know, it's not a big helicopter. The blades are probably about this big. Has a nice camera on it, but this was the camera from from Perseverance that what took the video, and so we got to actually see it happen. It has now conducted 28 flights on the surface of Mars. The intent was to do 5 and demonstrate the technology, and you're done. But the scientists have found that because it can go out ahead of the rover with its cameras and scout, and it can also go into places the rover can't get to, like kind of up on steep hills and take pictures up close, that it's actually turned into more of a scientific tool for the scientists. So we really have demonstrated, number one, that you can do it, but also number two, that it's value for science. And I would anticipate that future missions to Mars will certainly have this in mind. And I would assume that once we have humans on Mars, they'll have a fleet of small helicopters to go out and do things for them as well. So a great achievement, and first time ever. So we're excited about that. And here you can see, actually, like I said, we're up to 28 flights since we built this slide. And as I said, this is kind of where we've been with the rover and the helicopter. And as I said, we're actually now headed back up to the river delta. So this was the 26th flight up in this area, and then 27 and 28 have been on up in here. So very, very successful, and I think paved the way for future aeronautical missions on the surface of Mars. So let's move beyond Mars, out into the solar system. Jupiter class, the next planet past Mars is Jupiter, right? And so the largest planet in the solar system, the first one that formed in the solar system, the planet that probably protected the Earth from asteroidal bombardment and allowed us to actually create life here because it sucked up all the bad stuff that was going on in the solar system at that time. So Juno is our mission to Jupiter, our current mission to Jupiter. Went into orbit around Jupiter back in 2016. And its mission really is to peer below the clouds and understand more of the interior of Jupiter. What's the composition of the atmosphere? What's going on with the wind currents and those sorts of things? How are these bands moving around? And just really give us some fundamental knowledge about this first formed and largest planet in our solar system. So again, great success. This is our first solar-powered mission out that far to Jupiter. Our previous mission out to Jupiter, called Galileo, had to use nuclear power, which is basically plutonium, which decays, generates heat. We turn the heat into electricity. But because the solar cell technology has dramatically improved in the last 2 or 3 decades, we're actually able to fly spacecraft around Jupiter with solar power. And I'll talk about our next mission out that way, and it's also going to be solar powered. And that's Europa. Europa is a very interesting moon around Jupiter because it's a water moon. You see that surface there? That's all ice. So you've got ice on the surface, but literally beneath the surface you have liquid water. And you say, well, how could there be liquid water out there where the temperatures are like minus 200 degrees and so on? Well, what happens is Europa is orbiting Jupiter, and the tidal forces as you orbit Jupiter, basically because it's not a perfectly circular orbit, literally compress and expand Europa as a moon. And that compression and expansion generates enough heat to keep the water underneath the ice liquid. And scientists believe that there's probably 2 to 3 times the amount of water on Europa as on the entire Earth. So just add the Atlantic, the Pacific, the Indian, every ocean you can think of, and multiply by 2 or 3. And that's how much water is on one moon that's orbiting Jupiter. You know, back when I was taking science many years ago, we thought Earth was probably the only place that had water in the solar system. Now we've found water all over the solar system. So very exciting for the scientists, and in fact, I'll touch on that again in here in a bit. So this is our next major mission out to the outer planets, called Europa Clipper. So it's going to go back to Europa and investigate that moon in a much more detailed way than we've ever done in the past. Essentially, it's going to have ice-penetrating radar, it's going to have spectrometers, it's going to have high-definition cameras, it's going to try to understand what is all this weird red lines and stuff made of, it's going to understand how deep the ice is, it's going to give us a lot of information about kind of how this whole moon is constructed. Again, because where there's water, there could be life. And scientists are always interested at NASA in could life have formed elsewhere. And so that's what we're building right now. If you came to JPL today, you'd see a lot of the pieces of this in our clean room getting assembled. We just started integrated assembly and test, as we call it, about 2 months ago. So the spacecraft is coming together, and we're on schedule for a late 2024 launch to head out to Europa. Saturn is the next planet out, and we don't have a current mission flying out there, but Cassini was our mission that went out to Saturn, launched in '97, took about 7 years to get out there, and then operated until 2017. So roughly between 12 and 13 years of operation around Saturn. And you know, all those incredible pictures you see of Saturn's rings and everything else were taken by Cassini. And you can just see some of the findings here in terms of Titan and understanding the cycles on Saturn. And Enceladus is one of those moons of Saturn. And this is literally pictures from Cassini as we flew through these jets of liquid water that are coming up out of the moon's crevasses. So Enceladus is another one of those water moons. And unlike Europa, which we haven't really confirmed that there are any kind of liquid jets coming out, Enceladus is actually shooting out jets of liquid water periodically into space. And so our navigators that were flying Cassini at the time figured out how they could literally fly Cassini through one of those jets about 30 miles above the surface of the moon, and with the instruments we had, capture information about the composition of the water that was coming up out of the interior of the moon. And so because of that, we do something in the US called decadal surveys, which define for the next 10 years what are the top science priorities in various areas: earth science, planetary science, astrophysics. So the planetary decadal survey just came out about 3 weeks ago, and going to Enceladus was the number 2 priority in that decadal survey. So because it's a water moon, because those jets are shooting up out of there, then we can easily fly through them. They want to come up with this concept called an orbolander, which will essentially orbit multiple times around the moon and eventually land on the moon and take samples. So that will be another flagship mission, as we call it, in the next decade that we'll start working on. I kind of skipped over the asteroid belt, but I want to talk about that because we're going back to the asteroid belt as well with a mission called Psyche. Psyche is believed to be an all-metal asteroid. It's the 4th largest asteroid in the asteroid belt. And you think of asteroids, you think of rocks, kind of big rocks. Well, really, the 4 or 5 or 6 or 7 largest asteroids are really planetoids. They're kind of small planets. So Psyche is one of those planetoids. And what scientists believe is that ultimately it probably had some kind of surface that over time asteroidal bombardment just kind of stripped all that away and essentially left the core of this planetoid. So you've got this theoretical metal core that we can now go out to and examine a planetary core directly. So that's why it's exciting for the scientists. That's why we want to go out there and see what a planetary core might be like. That's an all-metal core. And so that's our mission called Psyche. I've already told you all that, but here's a picture of the spacecraft in our clean room about 2 months ago. And we just got it all buttoned up, and we shipped it down to the Cape on an Air Force C-17 about 2.5 weeks ago, down to Cape Canaveral. So it is currently down at Cape Canaveral. We're doing all of our kind of pre-launch processing down there, and then we'll launch it in September, headed out to Psyche to do that exploration. And now, quickly, we'll go beyond the solar system. As I said, we do a lot of astrophysics. We look out beyond the solar system. I think you heard in Susie's bio some talk about some of these telescopes. So the wide field planetary camera, JPL built that on Hubble. It's the camera that corrected the out of focus astigmatism that Hubble had. So it allowed us to get all the great pictures from Hubble. Spitzer is an infrared telescope that's done incredible mapping of the universe in IR. NEOWISE, this was a near-Earth object. It was actually an infrared telescope, but it ran out of coolant, so we turned it into looking for near-Earth objects like asteroids that could be headed toward the Earth. Still conducting that mission, and I talked about the X-ray telescope already, NuSTAR. This is our next telescope. You say, well, that doesn't look like much of a telescope, but that's just the baffles on the end that keep the light from getting into the telescope itself. And this is an infrared telescope that's going to do an all-sky survey in infrared, which we've never done. Spits are pointed at various different areas of the sky, but to do an all-sky survey in infrared has never been done from space, so that's what this telescope will do. And you can see all the different things it's going to do there over 6 months, and that's on schedule for launch in 2024. Oops, back up here. So we all have seen that James Webb Space Telescope has launched and is operating, doing great in terms of getting everything in focus. This is the next big telescope for NASA called the Roman Space Telescope and the coronagraph. Well, what is a coronagraph? A coronagraph is a device that goes inside the telescope that allows you to block the light of a star that you're looking at, and then that allows you to see the very dimly reflected light of any planets that may be orbiting around that star. So the coronagraph blocks the star's light, and then we can see that very dim reflected light from the planets. And why is that important? Remember, we talked about exoplanets. So this is the first time we would be able to actually directly image or see an exoplanet. And when you can bring the light in of an exoplanet into your detectors, now I can do spectroscopy on that light. I can break it down into its components, and I can tell you the composition of the atmosphere and what's going on that planet. So is there methane there? Is there nitrogen there? Is there oxygen there? Does that indicate that there could be life there? So a very important capability that we've never had. So the telescope itself is being built and managed by the Goddard Space Flight Center out in Greenbelt, Maryland, and the coronagraph is being built there at JPL, and that's the component that will allow us to do that exoplanet imaging in the future. And again, scheduled for launch here in about 4 years. And of course, the Deep Space Network, I always like to end with this because it's one of the reasons I come here to Australia is because we have the Deep Space Network site out in Canberra. Really a workhorse in the southern hemisphere for us. And without the Deep Space Network, again, none of this data comes back, none of the science gets done, and it has to be extremely reliable day in and day out. In fact, they normally maintain above a 99% reliability in terms of operating every day and getting the data back to the scientist ultimately. And Canberra is the only site that can service Voyager 2, and I'm sure Susie will tell you all about that. And this is just, we have a lot of partnerships across Australia. We had some great partnerships discussion here today with the university. We partner with CSIRO. We partner with the Space Agency. I'm not going to go through all these, but it really is a tremendous partnership between NASA and Australia. I know the Space Agency has just signed some future agreements. We signed the Artemis Accords together. So things just continue to grow, partnerships just continue to grow, and I think it's just an incredibly exciting future for space writ large when you look at all that's going on, but also for the partnership between the US and Australia and for space in Australia. Finish up with just our next missions. We've talked about SWAT. EMIT is a mission that's going to measure dust coming off of Africa because that flows over the United States and dramatically impacts our climate. We've talked about Psyche. On Psyche is the Deep Space Optical Communications payload, which will first time do laser communication out from the outer planets. And then we have several other smaller spacecraft that will launch in 2023. So we'll have some questions and answers at the end. I'm kind of open to stay as long as you want, but I'll turn it over to Susie to tell you all about Voyager. Oh, and you need the mic.
Perfect. I can hear myself whispering. All right. Well, good afternoon, everybody, and thank you for hosting us from JPL here today. I'm going to stick this in my pocket, I think. Okay. So I was introduced, I have two hats that I'm going to talk a little bit about both today. I am the project manager for Voyager, and just for a show of hands, how many people are under 45? I'm not under 45. So it's about more than half, maybe 2/3 of the audience. So you were born after Voyager was launched. That means that maybe your parents told you stories about the Voyager spacecraft. If you're older like I am, I was trying to get my driver's license about the time that Voyager was launched. It's the oldest operating mission anywhere in the world. It's also the furthest in distance, and we'll talk a little bit about that. And then I'm going to talk about how we talk to these spacecraft, which is through the Deep Space Network, which is the other role that I play at the Jet Propulsion Laboratory. And in reality, Voyager and the DSN grew up together, because as Voyager got further away, we had to make more and more enhancements to the Deep Space Network to be able to talk to these spacecraft. So Voyager was originally a 4-year mission, okay? It was launched in 1977. If you're familiar with the Bee Gees, they had the #1 hit in 1977. How Deep Is Your Love? I'm sure everybody's familiar with the Bee Gees, right? Australia. Its original mission was a 4-year mission to Jupiter and Saturn. That's how it was designed. That's how it was built. There are actually 2 identical spacecraft. They're on slightly different trajectories. Voyager 2 was actually launched first, and Voyager 1 was launched 2 weeks after that. The numbering is based on when they got to Jupiter. So even though Voyager 1 was launched second, it got to Jupiter first, which gives it its name. And we were able to do, because of the success of the Jupiter and Saturn mission, we were able to continue Voyager 2 out past Uranus, which is when I got involved with this project. My first job out of college was on this mission. So Voyager 2 went on to Uranus and then out past Neptune, and then just kept going. And we'll talk about the kept going part here in a couple minutes. But Voyager is the only spacecraft that's been by Uranus and Neptune, or not only just both of them, but any of those, Uranus or Neptune, either of those, there's no mission that's been there since. So all the data that we know from an in situ type thing is from our Voyager spacecraft with our lowly 1977 technology, 64K memory, less than what your car fob has. Every time you open your car door, think that the Voyager spacecraft has less memory in it than what it's taking to start your car with. But Voyager's been going now. It will be our 45th launch anniversary this summer. And so we've been going since 1990, traveling out through the heliosphere, out past the termination shock, and then finally out past the heliopause. So it's in a really incredibly important position in space. We are the only mission that does in situ data. And NASA has what they call it's a heliospheric system observatory. And basically it's a lot of missions that are studying the sun. But Voyager, and both Voyagers are in interstellar space. We play a key role in that. Because of the in situ data, it's a multidisciplinary type data, and most of the other missions that are looking out at the heliosphere are in an Earth orbit, and they're looking out. And so they need our data contributing to that to be able to make a better model of our sun. And right now, our VIM is a Voyager Interstellar Mission. That's what VIM stands for. For Voyager 2, we have 4 instruments that are operating. In Voyager 1, we have 5 instruments. The difference being the plasma wave, the plasma wave instrument. Now these 3 of those instruments, the ones on the right-hand side of the screen, are out on a boom. And they're very cold because as we lose power, Larry was mentioning Voyager, no solar power, no solar panels. It's all the RTGs, radioisotope thermoelectric generators. They degrade, it's plutonium-238, they degrade at 4 watts per year. So as we lose power, we're really getting toward the end of this mission. And we've been required to turn off instrument heaters in order to save enough power to send the signal back to the Earth. And our signal is not very strong, 160 bits per second, so it's not a big signal. But losing 4 watts a year, we're down to the point where we've got to turn off heaters. And we've been turning off the heaters on these instruments, and the instruments still work. They get 50 degrees C colder, but they're still operating. So they're operating at temperatures that are lower than what they were designed for, and where they've never been tested. So it's really quite remarkable engineering. That's all I gotta say. It's really, really remarkable engineering for this spacecraft. Okay, if you're an engineer, you love problems, and this is a challenge. We have super long round trip light times, over 20 hours to get the signal from Canberra to the spacecraft, and 20 hours back. It's almost 2 days round trip to get information from the spacecraft. So we have to design simplified onboard blocks. They're repetitive. We don't do a lot of commanding to the spacecraft. The spacecraft has to be able to safe itself. It has to be very autonomous. I have that built in there. And we operate in a mode where we're always sending data back down to the Earth. It's just that the antenna is actually looking at it that we capture it. So that's our operations mode. Over 45 years, you can imagine that most people that built this spacecraft are no longer here with us. And so it's very hard, that knowledge capture of how the spacecraft operates is important. But when the spacecraft was built, everything was typed on a piece of paper, right? So we've spent years scanning in documents, but you still lose what those engineers had in their heads and how they developed operating the spacecraft for the first 20 years of the mission. And so it's a challenge, and this is a chart that I put together for a talk on an interstellar probe mission. So if you want to send something out there to 500 AU and you're going to take 25 years to do that, or 30 years to do that, what are the challenges? And we deal with these every day. We only have 12 people on our flight team that are flying 2 missions. So it's a small group. We really have to reach back into your Rolodex and try and find people whenever you have a problem that might know something about that. So I mentioned that we lose 4 watts of power a year. So every decision that we're making now is a trade between risking the life of the spacecraft and leaving enough power in order to operate the transmitter. But we also want to avoid freezing the spacecraft, because we need to be able to point that antenna at the Earth to capture the data. And if the hydrazine in the propellant line freezes, then we'll slowly drift off and we'll lose the signal. So we've adapted things like using our DTR, digital tape recorder, has a heater. Okay, on Voyager 2, we're not recording any data anymore, but we're leaving it on because it's strategically located where it's a good heater for our propellant lines. And so it's really that out-of-the-box thinking that kind of makes this project fun. But again, we have no hardware test bed anymore, and lots of things that you expect of a regular spacecraft we don't have to help us. It's just our own ingenuity that we can think about how to keep these spacecraft operating as long as possible. And here's just a few little statistics. I mentioned the one-way light time in the middle and the round-trip light time. They're very fast spacecraft, 38,000 miles per hour. Voyager 1 is the faster of the two spacecraft, so its distance from the Earth increases. It's a steady state, but it's gradually separating as far as Voyager 2 will never catch up with it, I guess that's what I'm trying to say. Voyager 1 is the faster of the two spacecraft. And you can't forget the gold record. This is the only slide I have with the gold record on it. But I think that's what makes Voyager pretty iconic, is the gold record with the sounds and the images from the Earth that Carl Sagan put together and put on at launch. And it really helps connect humanity here on Earth to this mission. Not just Star Trek, but actually the record here. Okay, and this is an interesting image of our trajectory. It was mentioned it is true that Voyager 2 we can only see it from the southern hemisphere because its trajectory was down and out of the plane of the planets, and Voyager 1 is actually up and out of the plane of the planets. And we have, you can see that I don't want to say if we have a goal, but we believe that we can keep this spacecraft operating at least to its 50th anniversary, probably both spacecraft. And if we're blessed with good engineering decisions and a very robust spacecraft, we might be able to get it out to 200 AU. So that would be quite remarkable. It would be out in the 2030s if we got that far with one instrument on each spacecraft. I also point out on this chart where New Horizons is. New Horizons is a mission that went by Pluto and it's kept going for several years now. It will never catch up to Voyager though, because it's not going as fast. And it's key for us we have to talk to the Deep Space Network. Larry mentioned this earlier, but the Deep Space Network is located in 3 places. And we have the control center at JPL. I think we went through this already. And these are these locations. 2 are in the northern hemisphere. The only one in the southern hemisphere is right here in Australia. And we've gone to a model for efficiency to do what we call follow the sun. And I think one of the talks we talked to today, somebody was mentioning a follow the sun discussion. But basically what that means is that the antenna that is in sunlight, those operators are operating the other 2 antennas. So you just have a skeleton crew overnight when it's dark at an antenna, but the antenna that's in sunshine operates the other two sites. And that was probably not a technical thing to resolve. It was probably much harder to resolve all the politics of having governments operate other government antennas. Edward Cruzenseer was really involved in getting that going. So what are we doing? Well, we're expanding the Deep Space Network. We have 2 new antennas in Madrid. One was opened in 2021, right in the middle of COVID. Nobody got to go, no great ceremony or anything. You can see everybody with their COVID masks on. And one just a year later, in 2022, still COVID masks, but a little bit better. The King of Spain came to that opening. So there's currently actually 6 antennas in Spain. And one of the things we've done for Voyager is they did an array of 5 antennas to get the data back, the playback data back from Voyager 1. That's the first time the Deep Space Network has ever arrayed 5 antennas at one site. And what we have coming up is we're building another new antenna here in Goldstone, which is out in the Mojave Desert. I think if you've been out to CDS-CC, the whole might look familiar. These are antennas. The 34-meter beam waveguide antennas have all the electronics in the ground. Okay, so you dig a hole, and you make a pedestal, and then all your electronics sit in the ground. And then you just put the antenna structure on top. So it doesn't sit up high, that high off the ground. But it's coming along quite well. The other type of activities we're looking at for the Deep Space Network include, we mentioned the new antennas, but we're moving to higher frequencies, going to Ka band. X band is crowded, S band Sierra band is extremely crowded, but we're trying to get missions to move to Ka band and then to optical. And we have a project at our R&D antenna, which is optical communications in the center of an RF antenna. And the middle picture there you can see is our 7-segment optical detectors that are mounted on our R&D antenna out at Goldstone. And in the future, when it's all done, it will look like the bottom picture, which is an 8-meter segment of optical mirrors inside the RF. And that's where we like to go. You know, optical at Mars distances, deep space, is where we're planning to head out and do. And the Psyche mission that Larry mentioned has a optical demonstration on it for deep space optical. And it will send data back to that middle picture there, that 7 segments test mirror that we have. So just to wrap it up, you know, Voyager's got great breakthrough discoveries. It started as a planetary mission. It then became a heliophysics mission, and it's literally now an astrophysics mission. We're out into the local interstellar medium. The data that we're capturing on the plasma density and whatnot is astrophysics data. It's providing unique data. Think about how long it's going to take to get another mission out to where Voyager is. So that's why it's extremely important to keep these missions operating as long as possible. It's also important to have 2 spacecraft. That helps the modelers fit their models to what they think is happening with the sun and with the heliosphere. And I mentioned at the beginning that the Deep Space Network and Voyager really grew up together. Between the Saturn flyby and the Uranus flyby, the big 70 meters antennas, they were originally 64 meter antennas, and they extended them to 70 meter to get the Uranus data back. And then at Neptune, we started to array antennas together. And I think here in Canberra, we arrayed the 70 meter with a Japanese antenna to be able to get the data back. And they really developed antenna arraying for Voyager too. So a lot of technology that we have in the comm world on the ground came about to help support the Voyager mission. And I mentioned that we expect to get to 50 years of launch and hopefully, or maybe possibly out to 200 AU, which would be outstanding. And again, thank you all for coming, and I think Larry and I can probably answer whatever questions that you have. So.
So Nelson and I can hand microphones to anybody who has a question for our two guests here. So just raise your hand, and we'll bring you a mic.
Stunned silence.
Or you can just yell really loud, but up to you.
Thank you for coming. It was a really interesting presentation. You mentioned a little bit about autonomous navigation, guidance and navigation, especially with AI coming into the future now, being more prolific. Could you elaborate a little bit more on what kind of AI you're looking into for this kind of autonomous navigation?
Yeah, again, I did mention in the context of Perseverance, putting a lot of capability to drive autonomously, and we did learn that. We had some on Curiosity, but we recognized that for Perseverance, in order to capture all the samples we wanted to capture in the time frame we had been given, we had to be much more efficient in our driving. And so that's what led to improving the capability using the onboard cameras, developing the software, the machine learning, everything that had to go into that to allow us to drive safely. And I think for us, in terms of future AI, when you think about missions to Europa, missions to Enceladus, missions when you're way out there, and for example, we've done some Europa lander studies where, again, you heard Susie talk about light time. Well, it's hour to whatever it is, I don't remember, but it's a long time to get out to even Saturn or Jupiter with light and commands. So if you've got a lander on the surface of Europa, which is probably, at least with the technology today and what we could afford, would be battery powered. So it's not going to last forever because you don't have a lot of solar energy to charge the batteries. So now you've got a short duration mission. It has to land and do a lot of things on its own. And so I think that for us is one of the biggest drivers with respect to AI, is these incredibly complex missions that are really in places where we can't interact in a real-time basis or even on a short time frame basis. So the machine has to do a lot of all the thinking on its own. The other component is with respect to just the incredible amount of data that we're gathering with these missions now, and how do you handle that data, and a lot of it we think is going to have to be on board. So you're going to have smart processing that will allow us to say, this is important data, I should downlink it, I can store this, or I can just, it's not needed or whatever. So it's I think the combination of those two things that really drive us to think a lot about machine learning and AI and operating in those kind of environments.
Thank you.
Sure. And we have a whole team at JPL focused on AI and ML in a big way.
Okay, just a,
Yes,
a question over here, and possibly a little bit tangential, but you did mention humans on Mars, and we were fortunate enough to have your immediate predecessor here last week, so Charles Alachi.
Yeah.
I was having a chat to him, and he mentioned that obviously, and you have shown, and through the stunning work of yours and others, the technologies we have, we're able to get to Mars, and perhaps even getting to the point that now we can develop those to get humans to Mars. But he was saying that the life support technology is the real showstopper. So are you able to elaborate on that, in terms of the grand challenges that there are to keeping humans alive, say on Mars? And I've got my own views on that, and certainly of NASA, but I'd like to hear them from you and see what challenges we have to keep humans alive.
Yeah. Okay, sure. I think challenge number one is just getting to Mars in the radiation environment, right? Because as you all know, we're protected here with the Van Allen belt and all those good things that keep all the bad things away from us. And so when you're traveling several months to Mars, you've got radiation. So, shielding and all those things, okay, but that's complex, and that adds mass and all those sorts of things. So that's, I think, problem one. Problem two, once you're on Mars, you've got the same problem on the surface because there's very little atmosphere, as I said, 1%. There's no magnetic field. So now you're still getting all the solar stuff, you're getting all the cosmic stuff. So I've got to deal with that. Either I've got to build a habitat with shielding, or I've got to go underground. So now or I just stay a short period of time. So if I'm going to stay there longer, I've got to do those things, but then I've got to have the equipment to do that. So it's complex. I mean, it really is, in terms of protecting the humans and then just providing the resources. I mean, in the NASA model, you send all the resources out first. The habitats that can protect you, the food, you've got to have, rocket fuel to get off the surface, all those things. So it's a combination of hard problems. Now, Elon will say that he's going to land 50 tons on Mars with his Starship. And I mean, I'm all for that. I mean, if an entrepreneur can come up with a way to deliver that amount of cargo to the surface of Mars or the moon, it does change the dynamic. If I can put that much stuff there, I can send a Caterpillar tractor there, and or whatever. And so who knows exactly where this is going to go, but I think, and then there's just the physiology of the human body, long duration weightlessness, Mars is low gravity compared to Earth, and we've seen that kind of bad things happen when you do extended periods of time in those environments. So that's why NASA does do a lot of human physiology research to understand how this could all play out. So it's not just a simple thing to get there and really stay healthy as a human. I read a nice article that just asked the question, why not robots? I cannot profess an opinion on that.
I just wanted to ask, so is JPL doing anything in terms of space traffic management and sort of safety of flight in space, in terms of tracking, like with SSA, space situational awareness, and understanding the trajectories of RSOs and sort of dealing with them? Like, what is JPL's take on that?
In terms of space traffic management, SSA, that's not really our bailiwick, if you will. The thing we do talk about, and if you recall, I said something about NEOWISE, the Near Earth Object Wide Field Telescope. We worry about asteroid things coming toward the Earth, and so we have a mission called NEO Surveyor, which is a Near Earth Object Surveyor mission that we're in the process of working on right now. But in terms of tracking all the spacecraft in orbit, those sorts of things, we don't really do that. Johnson Space Center has a team that focuses on that. And then in my previous life in the Air Force, the team at Vandenberg Air Force Base at the Joint Space Operations Center does a lot of that. So we basically just take their data, like when we're going to have a launch, we have to do a collision assessment to make sure we're not going to hit anything on the way up. But all we're doing is taking the data from other organizations. But we don't, other than the near Earth objects, we don't worry about kind of tracking all those objects in space. That's other responsibilities.
Hi. Just the samples left on Mars, 8 samples that may be left there at some point. Is there a mission already underway planning to return them, or how hard will it be years in the future, or are we just going to wait for Elon Musk to wander up and grab them?
Absolutely. There's a mission called Mars Sample Return. It is underway. We're in the middle of the initial, we've done a lot of the initial design work. We're going to our first big review this summer. And so it is very complex. It's also been impacted politically by the Russian invasion, because it was a joint mission with the US and Europe. The US was going to provide a lander with the Mars Ascent Vehicle, the rocket that will take the samples off. The Europeans are providing the Mars Orbiter, which is the orbiter that will accept the samples and then get them back to Earth. And then they were also going to provide the Fetch rover, which is the rover that was going to land on another lander, drive off, go pick up the samples, and then bring them back to this container that would be put in the rocket. Rocket launches, rendezvous with the satellite, puts it in the satellite. Satellite uses electric propulsion to come back to Earth. All these things are in a container that then gets ejected. It crashes into the Utah test range at 3,000 Gs, and the samples survive. So that's the simple mission. But now it's become a little more complex, because with the European ExoMars mission, which was a partnership with Russia, they've now said, okay, sorry, Russia, we're not partnering with you anymore, but that leaves the Europeans in a bit of a lurch. And so they are looking at how do they execute the ExoMars mission, in addition to providing another lander and the Fetch rover. And that may not happen. So now we're in the process of looking at other options, which we have, to get the samples back. So stay tuned, but yes, the mission's underway, scheduled to launch in 2028. Samples would actually get back in 2033, roughly, 32 or 33. The reason it takes a while is because we're using electric propulsion to get the samples back from Mars, which is a pretty slow way to get back. But in terms of efficiency, it's very good, because you don't have to take a lot of mass in terms of fuel. So, but yeah, it's all underway. A little bit of perturbation with the Russian invasion that we're dealing with, but still on track for a 28 launch.
I have a few questions. I'm going to start the first one first. What are the key advices you can give to our students who would like to pursue career in space technologies, whether it's at NASA, JPL, or perhaps also Australian Space Agency or CSIRO? Maybe like from both you and Suzanne.
Well, I mean, first get the right education, right? I mean, you heard on the video, I mean, there's a lot of pathways into space. Obviously, a fundamental one is engineering, computer science, those sorts of things. So any of those STEM areas, I think, have applicability to the space world. So it's, first of all, just kind of where do you want to be in terms of what education you pursue, and then really figuring out ways to get involved. We have internships. We bring in, foreign nationals into our intern program, partnering with people that are already doing this kind of work when you're an undergraduate or a graduate student, and just getting involved in all of that can definitely, provide you with opportunities. I know in the U.S., I think the latest numbers I saw in the aerospace industry is like we're 300,000 people short in terms of what the need is over the next couple of years. So I think there's definitely a demand signal here, and we were talking earlier today that I think the demand signal in Australia is continuing to go up. So I think there's definitely opportunities, and it's just focusing in those particular areas that frankly are employable in that particular domain. But Susie,
and I would add to that there's opportunities to come in from what might not be traditional careers. You might be an economics major but decide that you really like space, and if you've got a certain amount of math background, you can make that work. And one of the things that working at JPL is there's a wide range of things you can do at JPL, and if for your career you're encouraged to go off and work on different projects, and you might be doing spacecraft commanding for a couple of years and then switch over to mission assurance, quality assurance. And if you get a little bit of background in software, then you might be writing software. And that, being able to experience all those different areas makes you, a better employee to JPL, or if you're just at a space company. We encourage, at JPL, we encourage you to go broad, as well as, taking on more responsibility. And I think there are opportunities to get into space from more non-traditional careers because there is such a shortage. There is such a shortage right now.
Yeah, I had a question. What elements of the Voyager spacecraft's design made it so successful to have such a long lifespan with antiquated electronics from so long ago?
That's a great question, and I think in part it wasn't quite so pushed for budgets the way missions are nowadays. It was given more lenience. It was given a healthy budget when they built it, so you could build it very robustly. And the engineers, I've read stories, the original engineers, when they built Voyager, they didn't skimp, and they didn't necessarily tell their bosses what they were doing, but if they could get a higher rated part, a part that would last them 12 years instead of 4 years, they'd go out and get that and put it in. They all had a vision. They had a vision of where this mission could go, and they weren't quite so constrained as we are nowadays with NASA on their budgets. And it's a fabulous mission. There's nothing more you can say than that.
So, sorry, just to ask again, does that mean that spacecraft missions now are not run the way that they were then? What elements, so I suppose you said economically they had a larger budget, but how is that not the way things are run now if it was so successful to keep going?
Well, NASA has a lot of extended missions, but they all vie for a small piece of money. So, quite frankly, one of the things that keeps Voyager going is that gold record. Everybody in the world knows what that gold record is. And I'm sure if NASA said, we're not going to fund you anymore, we could crowdsource that spacecraft. No, probably get 3-4 times the budget that NASA gives us. But so, attaching your, this is not so much for, well, it's a different part of longevity, right? It's attaching your mission to something that the general public likes, that inspires them. You've got this time capsule on your spacecraft, and it's just going to keep going and encircle the center of the galaxy. That's very inspiring to people. And I heard more than one person say today that Voyager was what got them into the business, right? You want your missions to inspire the next generation. I certainly think that helicopter is going to inspire the next generation. But when you're out designing missions, think about what it means to the next generation, and how could your mission, help inspire STEM and space to the next generation also.
And I will say that the reality is, though, that the missions generally, even today, still last a long time and usually beyond their design. I pointed out Curiosity, which really was designed for 5 years to operate, and we're going on 10 years, and there's really no major issues with it right now. And the other component I would say is just complexity. I mean, you compare a Voyager to a Curiosity, it's orders of magnitude more complex. And as you introduce more complexity into a system, you have more opportunity for faults and things to happen. So
that's true too.
There is that scenario where Voyager, looking back, it's old technology, but it was a simple spacecraft in reality. So I think that's part of it as well.
I have some question about the partnership between Caltech and NASA. Prior to my role at the University of Adelaide, I was also in the US system. I've been very impressed with one of the things about where they have a good partnership between the National Laboratory and the university. For example, Lawrence Berkeley National Lab with University of California, Berkeley, and Caltech with NASA. So do you see this opportunity for us? And what are the challenges? Obviously we see the impact that we have seen from this partnership. But one thing that we see here is also ASA, Australian Space Agency, is located adjacent to the University of Adelaide. Likewise, we also Defense Science Technology Group is also located not too far away, within the same half distance, by car, half an hour distance by car from the University of Adelaide. So do you see this actually a very important part of driving the innovation as part of having national laboratory? In your case, would be NASA JPL with Caltech. Likewise, it's going to support the university as well.
Yeah, I think if you go back to our history in the U.S., the federal labs were started after World War II, when it was believed that you needed a long-term research lab that could operate and focus in those arenas, whatever those arenas were, whether it's nuclear power, nuclear, whatever it is, to really be consistent, to bring in the best minds, and to, support where the nation wanted to go in a particular area. And I think that's still a powerful construct with academia and a government agency with that research arm providing that consistency, that long-term view, and bringing in the people who can do that type of research. And so University of Adelaide, and you're ideally placed to be a research lab, those kind of functions here in Australia. So for the U.S., it worked very well because, again, it was recognized that the government, people came and went, and we just wanted a long-term organization that focused on research in a particular area, whether it's JPL or Lincoln Labs or MITRE or Lawrence Livermore and Sandia. I think they've all been incredibly successful because of that model that works.
I was just going to ask if we had any more questions here. Anybody?
Hello, just touching on the Deep Space Network, you mentioned that as it got further, you managed to communicate with it by arraying the satellites from one in Australia and one in Japan. How exactly did that mechanic help? Was it just collecting more data?
Yeah, that's exactly right. It's collecting, it's taking the signal that comes down in Australia and the signal that comes down approximately the same time in Japan, and then pairing them up and matching them together. So.
Yeah. And we do the same thing at the sites. I mean, we may array 4 antennas at the sites, so you get all that data, and then you have to combine it. So it's essentially the combination of the data you're getting from wherever time phase, and then you combine it and you pull out the signal.
Right, okay, thank you.
I do have a question about that, Susie. I think you presented that, you mentioned that there are 6 of this to be established in Spain. Is that true?
There's 6 right now. Well, each site has at least 3 34 meters that we're building out to 4, and then 1 70 meter. But the Madrid site has 6 because we kept one of the older antennas operating because we're going to take one offline. So it's.
I see.
Yeah.
Okay. So while in Australia, in Canberra, we only have 1. Is that true?
No. You have 3 34s and a 70 meter, and you're
Okay.
going to get a 4th one in about 6 years.
Sounds good. Fantastic.
34 meter, and we've got another 26 meter, which was the old moon antenna from Honeysuckle Creek.
So the baseline is 170 meter and 4 34 meters.
Yeah.
And we've been upgrading the 34 meters or building new ones. Yeah. I think there's a question here.
Well, while we're talking about baselines, have you looked at sending a bunch of CubeSats around, say, Mars, to all have a telescope to increase that baseline? So, while looking at that gravitational instrument, you've really managed to nail getting the alignment correct. So if you send a heap of telescopes in form of CubeSats spread around Mars a bit more, you can quite easily get a much larger baseline to get like a much finer resolution. Have you looked at this?
I won't say explicitly that we've looked at the telescopes around Mars, but we're definitely looking at, the ability to link multiple spacecraft together to perform a mission. So I will give you one example that we are doing, which is essentially building a virtual RF antenna using 6 CubeSats. So it's a mission called Sunrise, which we will put out away from the Earth. I don't know if it's at the Lagrange points or not, I don't remember, but essentially you've got 6 CubeSats in a formation that are creating a virtual low-frequency RF antenna, large antenna, that will look at the sun and measure the low-frequency radio wave that comes off of coronal mass ejections from the sun. And that's important because if one of those big CMEs ever head toward the Earth, it's pretty devastating. But the low-frequency radio wave gets to the Earth much faster than the CME, but you can't detect it on the Earth because the atmosphere filters out the low-frequency radiation or the low-frequency signal. So we're going to put this thing up in space, stare at the sun, monitor CMEs, and we can tell you when they're happening before the actual coronal mass ejection gets to us. We are arraying CubeSats to do that. And I know there's ideas on the board to do that with optical as well, but we haven't really put anything up yet. But it's a powerful tool that I think will happen.
Okay, thank you.
Do you have one more last short question? Oh, yeah, please. There's one more.
So thanks, Larry and Suzanne, for the fantastic talks. I have a question about the deep space networks, particularly the optical comm. So I'm wondering if this optical comm tech is custom built or off the shelf, and what is the state of development of this optical comm?
Well, the deep space optical comm is custom built for right now at JPL. The detectors are built at JPL. We do have some industry partners that are helping us. But if it goes well, then we can pass, one of the things about an FFRDC is we can pass that technology off to industry. That's the whole purpose to developing technology at a place like JPL is that we develop it and then we give it away. So, but in the short term, it's all designed and built at JPL for the most part with some industry vendors, but it's one of the kind. It's not off the shelf.
All right, thanks for that. As far as I know, this technology is not mature in the market yet. Am I right?
That's correct.
Yeah.
Although the low Earth stuff is getting there.
Yeah, the low Earth LEO kind of laser comm, there's a lot of capability out there today. It's the deep space component that's new, and that's why we're demonstrating this on the Psyche mission. So building the transmitter and receiver that will fly on the Psyche satellite, that's all new technology because just of the distance involved and the light time, even though it goes pretty fast when you're out at Mars, you can't point to the receiver because the receiver is going to move in the time the light gets to the Earth. So there's a whole mechanism of how you actually transmit the laser from Mars or beyond to the Earth and how that all has to operate that is being developed at JPL. But the nearer stuff is actually coming more into just, you know, is it off the shelf? I mean, you could go to a contractor today, the right people, and I think you could get that capability for your spacecraft.
All right. Thanks,
Yeah.
Suzanne and Larry.
Sure. Okay, well,
So
again,
thank you
our
so
honor.
much. Larry, Suzanne, thank you so much on behalf of the University of Adelaide. We greatly appreciate your fantastic talk and also your wonderful visit here. I hope you greatly enjoy your visit and time here. But also on behalf of the School of Electrical and Electronic Engineering and also Andy Thomas Center, we greatly appreciate the audience attendance here. We learned a lot from this talk. We also would like to appreciate, thank you for our collaboration between the school, in particular Space Electronics Group in our School of EEE, with like the NASA JPL scientists and engineers for the past year. That has been fantastic. I think we should continue to do a lot more this year to support our ASA-funded project in both remote sensing by optically connected CubeSats and next generation phased array antennas for deep space networks. I think it's actually fantastic, and we should really not only strengthen the partnership, but also like develop new partnership opportunity with the University of Adelaide. Thank you again.
Our pleasure. Great to be here. Thank you all.